We're very happy today to have Shaoyun Bai from Princeton talking about Rouquier dimension quantitative intersection of skeleta and Orlov's conjecture.
All right, thanks. So thanks for the invitation. It's my pleasure to speak here in the Western Hemisphere Virtual Seminar. So today, the title of my talk is Rouquier dimension quantitative intersection of skeleta and Orlov's conjecture. So this is based on the joint work with Cote, and there you can find a preliminary version of this on my website. Just Google it. So, all right, let's get started. So before I start the talk, let me give you an outline of this talk. So the first part of this talk is just about stating the main results I'm going to present today. So it has three parts. So the first two parts are about symplectic geometry, and most of the results are stated without using any categorical terms. While the third part of the main results is about algebraic geometry, and it could be stated without using any symplectic geometry. Then I will introduce the main notion of this talk, which is the Rouquier dimension of a triangulated category. I will recall its definitions and present some basic properties. Then I will try to state some properties of the Rouquier dimension of Fukaya categories and tell you how to obtain results in the first section using some properties of the Rouquier dimension of Fukaya categories. Then I will present some ideas of the proofs, which gives us some understanding of Rouquier dimension of Fukaya category. And if time permits, I will indicate some further questions along these lines. Okay, let's get started. So here's our setup. So assume that X lambda is a Weinstein manifold of dimension 2n. So here X is a smooth manifold and lambda is one form. So its Weinstein means that the differential of lambda, d lambda, is a symplectic form. Also, the Liouville vector field defined to be the symplectic dual of the Liouville one form lambda is required to be gradient-like for proper Morse function on X. Then we define an object which is called a Cx to be the union of cores of stable sum manifolds of X. So C here stands for core. And it's a fact that the set Cx is actually isotropic, and we call that the skeleton of the Weinstein manifold X lambda. So the question we want to understand is, suppose we are given a compactly supported Hamiltonian diffeomorphism of our Weinstein manifold, and we want to understand the intersection between the core Cx with its Hamiltonian push-off given by this Hamiltonian diffeomorphism. And we want to understand, can we get any quantitative lower bound of this intersection number? So that's the meaning of quantitative intersection of skeleton. So before stating our results, let me recall some basic results in this direction. So if we assume that the Weinstein manifold is subcritical, then we know that there's splitting disk, so we can just displace the skeleton Cx from itself. So in particular, for generic Hamiltonian push-off, there will be no intersection point between the skeleton and this push-off. As a special case, let's consider the Weinstein manifold given by the cotangent bundle of a closed smooth manifold. And we equip that with a Liouville form, which is a standard Liouville one form on the cotangent bundle. So in this case, the Liouville vector field is given by scaling on fiber direction. So we know that the core or the skeleton of this Weinstein manifold is given by the zero section. Then by the solution of Arnold's conjecture, in this case, we know that given a generic Hamiltonian push-off, this intersection number is bounded below by the sum of Bethe numbers. Then if we switch to more general Weinstein manifolds, we can just get the result that intersection number is non-trivial, is non-zero. In particular, it means there's at least one intersection point, provided that the Fukaya category is non-trivial. So this is original proof by Ritter using Rabinowitz Floer theory. So the problem is, in general, the skeleton Cx could be very singular, and at least it seems hard to me whether it's possible to develop a Floer theory for such objects. Okay, so here's the statement of one of our results. So let's assume that 2 times the first term class of Weinstein manifold given by 0, in particular, the symmetrical homology and the Fukaya category could define to be Z-graded. And let's assume that the symmetrical homology with coefficient over C is actually isomorphic to the affine coordinate ring of a smooth n-dimensional affine variety over C. So this is our assumption. So now assume that there is an object in the Fukaya category, namely a cylindrical exact Lagrangian, which has a gradient structure, such that if we look at the closed open map from a degree 0 part of symmetrical homology to the reciprocal homology of this object L0 itself, this is required to be an isomorphism. So know that the reciprocal homology here is not necessarily assumed to be concentrated at degree 0 a priori, but it is our assumption that this induces an isomorphism, which means that the reciprocal homology of L0 itself is concentrated at degree 0 after putting this assumption on the closed open map. So then our statement is take the skeleton of this Weinstein manifold and consider generic Hamiltonian push-off. Then the intersection number is bounded below by the complex dimension n here plus 1. That's the statement in this case. Now, if we consider the case where the underlying topological smooth manifold of our Weinstein manifold X is given by the cotangent bundle of a simply connected Lie group, but here the Liouville 1 form here is not necessarily the standard Liouville 1 form. So which means that the skeleton with respect to lambda could be singular in general in this case. But we still require that it's Weinstein homotopic to the Liouville 4 standard Liouville 1 form on cotangent bundle. Then our result says that this intersection number is bounded below by the rank of this Lie group plus 1. So here's a remark to the first part of this statement. So an object L0 as above is called a homological section, which appears in the work of Daniel Palmeriano. In particular, for certain kind of log-Calabi-Yau varieties, one can construct homological section using geometric methods. So that will actually satisfy the assumption here. So is there any question about the statements?
Are the two statements independent?
They're independent, but they're actually corollaries of a more general statement I will say later.
Thank you.
Okay, so let me move on to the next part. So which is about critical points of lattice vibrations over Weinstein manifolds. So let me give a rough definition of Weinstein lattice vibration. So it means that we are looking at this Weinstein manifold X lambda. So this vibration is just a singular symplectic vibration, but it just has many Morse type singularities. And we also assume that the restriction of this Liouville 1 form to the smooth fibers defines a Weinstein structure on the fibers. So such an object equipped with this projection map to C is called a Weinstein lattice vibration. So we are interested in the number of critical points of such a lattice vibration. So we introduce this notation, left W here stands for Weinstein, of this Weinstein manifold to be the minimal number of critical points of all Weinstein lattice vibrations over X lambda. So this is presumably a symplectic invariant or Weinstein invariant of the Weinstein manifold. So here's a proposition which joined with Kote. So the statement is there exists a pair of formally Weinstein homotopic Weinstein structures on the cotangent bundle of S3 such that they actually have different lattice number defined above. Okay, so this is about the symplectic part of our results. Now let me move to the Orlov's conjecture.
Sorry, can you go back to the previous page? I want to make sure I understand the statement.
Yeah, sorry.
Okay, but the underlying symplectic forms are different here.
Symplectic form, I'm not sure about symplectic form, but the Liouville 1 form is different. And they just stay inside the same, I can only a priori say that they stay inside the same formal homotopic class of the symplectic form, but not sure if the symbolic forms are actually isotopic.
So, but again, let me ask. Okay, so fine. You do not prove that these are symplectomorphic, but with different Weinstein structures.
I think I'm not asserting things that's strong. I'm just saying that our assumption just implies that their symplectic structures are formally isotopic.
I understand, because it follows from the Weinstein structures being formally isotopic.
Yes.
Okay,
Right.
thank you.
Yeah. Okay, so any other questions? Great, so let me move on to the Orlov's conjecture. So here is the conjecture for Orlov. So let's consider Y to be a smooth quasi-projective scheme of dimension n. So dimension is the Krull dimension or the dimension in terms of algebraic geometry. So then, yeah, the Rouquier dimension I will define later of this derived category of coherent sheaves over Y. So it's some kind of numerical invariance associated to this triangular category. The derived category of coherent sheaves of Y is actually conjectured to be equal to the dimension of the underlying variety Y. So this is a conjecture of Orlov. So this conjecture was conjectured maybe 15 years ago, and it has been proved for many examples by many others. So the list is too long, and sorry that I will now survey the results in this direction. So I will just instead state our results and pointing out the new cases we can cover. So here's a statement. So it says that Orlov's conjecture holds for any quasi-projective smooth, sorry, there's no smooth assumption here, for any quasi-projective variety over C, which admits a homological mirror given by a Weinstein pair of real dimension at most 4. So I will explain the terminologies here later on when we, after defining the Rouquier dimension. But let me just point out some new cases could be covered using our results. So the first ones are the examples from Hack and Keating's proof of homological mirror symmetry for log-Calabi-Yau surfaces. So it says that Orlov's conjecture holds for log-Calabi-Yau surfaces with the choice of the distinguished complex structures from the proof of homological mirror symmetry by Hack and Keating. And we see that Orlov's conjecture was already stated for smooth quasi-projective schemes. So it is known that it might fail in general. So there are examples of singular varieties that Orlov's conjecture, I mean the statement about its dimension of the derived category is not true. But nonetheless, for some examples, some singular varieties, Orlov's conjecture still holds. So we can find some singular surfaces which arise as mirrors of munar fibers from the work of Rouquier and Wood. So for these singular surfaces, it could be argued that the Rouquier dimension of their derived categories is actually equal to the dimension of the underlying variety. Okay, so this is a statement of Orlov's conjecture and our results. So is there any question? Okay, looks no. So let me move to the second part of this talk, so which is about the main object we want to study, that's the Rouquier dimension. So let's start with some setups. So I will use notation T to denote a triangulated category. Now we consider the notion of a generation time of a split generator. So it means that we say the generation time of a split generator of this triangular category is at most n if every object could be built from this generator, split generator G, by taking finite direct sums, shifts, direct summands, and at most n cones. Then the generation time of this split generator is just the minimum of all such n. The Rouquier dimension of the triangular category, which I use this notation Rdim, it's just a minimum of generation times ranging over all split generators of T. So in other words, it is a measurement of the complexity of the category in terms of how much cones you need to take to build every object from a given generator. So for our case of interest, so most triangle categories will come from, say, actually the derived category of derived Fukaya category. So given a pre-triangulated k-linear infinity category, for example, the Fukaya category of a Weinstein manifold or Liouville manifold, we define the Rouquier dimension of this infinity category to be the Rouquier dimension of the H0 of the category perfect modules over the infinity category. So in other words, if we're talking about the Rouquier dimension of Fukaya categories, we're talking about the Rouquier dimension of the derived Fukaya category. So this is the definition of Rouquier dimension.
Sorry, this definition, you're assuming there's a single split generator, or is it the definition will make sense if you require several generators?
Yeah, it still makes sense without a split generator. We just define it to be infinity if we can find one generating infinite steps.
But if your category requires like two split generators, do you sort of allow the minimum over all n over all sort of finite sets of generators or something like that?
Yes. So as I said in this bullet, the Rouquier dimension is minimum of all generation times ranging over all split generators. So in particular, if you have two, say, split generators, and you can associate the generation time to each of these two objects, you take the minimum of these two guys. And the point is you just range over all split generators and take the minimum of all of them. So if such a thing doesn't exist, we just say that Rouquier dimension is actually infinity. Yeah. Okay. So then let me state some basic properties of the Rouquier dimension. So the first property is about how the Rouquier dimension behave if we have a semi-orthogonal decomposition of our triangulated category T. So it specifies some sort of sub-additivity. So suppose that we have a decomposition of our triangle category T. So here from I1 to IM, they're all full subcategories of this T. And also they're semi-orthogonal in the sense that if we take two objects K and L, such that K is an object in a subcategory II, while L is an object of IJ, where I is greater than J, then we require that their Hom space is actually trivial. So this is definition of semi-orthogonal decomposition. Then the statement is the Rouquier dimension is bounded above by the sum of Rouquier dimension of each piece with a shifting by 1 here, but overall there's also shifting by -1. So this is the behavior of Rouquier dimension if we have a semi-orthogonal decomposition of the category. Okay. So secondly, there is some kind of monotonicity if we consider the quotient or localization of a category. So let's assume that C is an infinity category, and we take A to be a set of objects. Then we can consider the quotient infinity category C modulo A. Then the monotonicity says that the Rouquier dimension of C is at least the Rouquier dimension of this quotient category. So there is also another way to try to give an upper bound of the Rouquier dimension of the category C. So it's related to the notion of diagonal dimension, which was introduced by Elagin Lunts. So it says the following: if we have a resolution of diagonal bimodule, which is just an L-step resolution in terms of unetta bimodules, then the statement is the Rouquier dimension of C is bounded above by L-1. So in other words, if we have some kind of quantitative way of resolving the diagonal using unetta bimodules, that could give us the upper bound of the Rouquier dimension of the category. Okay.
But maybe you said this already. Is the first one an inequality, or don't you have an equality? Or?
It is an inequality, sorry, it's an inequality.
So you don't have any equality in general.
Not in general, but for some cases, yes. So take CPN with Balanson's collection, and this is true. Well, this is an equality, but in general, I don't know how to prove the equality. Okay.
I don't think you can expect it to be equal. I think if you take a direct sum, like an actual orthogonal decomposition,
yes,
then you will get something like the maximum.
Right. Yes. So. Thanks. Yeah. Okay. So there are some other properties of Rouquier dimensions I want to mention. So this is probably well known to others, but it's written down in the paper of Elagin. So let's assume that gamma is a quiver. In other words, it is a directed graph which is connected, finite, and emitting no loops or cycles. So then we consider the path algebra of this quiver. So K is a field we are working with. Then we can Rouquier dimension of the corresponding representation category of the quiver. So it says that the Rouquier dimension is 0, provided that gamma is actually of thinking ADE type. So otherwise, it's actually equal to 1. So there's another property which allows us to bound Rouquier dimension from below. It says the following. So suppose that the infinity category C has an object L such that the unital right module is proper in the sense that it's paired with any object defines a perfect module over the underlying field K. And also we assume that the cohomology, well, the self-infinity algebra associated to this object L is actually isomorphic to the exterior algebra of the vector space as infinity algebras. So assume that we have such an object. Then the statement is the Rouquier dimension of C is bounded below by R here, and R is a dimension of this vector space V. So the L as above is called a point-like object. So to justify its name, if the triangle category T, or actually DG enhancement, comes from, say, derived categories of coherent sheaves, then they actually arise from skyscraper sheaves. And for Fukaya categories, they can actually come from, say, graded exact Lagrangian torus. So yeah, these are two basic properties of the Rouquier dimension. So is there any question? All right,
so just a clarification. So for property 2, do we immediately learn that for coherent sheaves on a smooth variety, there's a lower bound?
Yes, not just for smooth ones, actually for yeah.
Indeed, because whenever there's a smooth point. Thanks.
Yes. Okay, there's a question from the chat. Should Elagin Lunts require category to be smooth? I don't think so. I think their proof actually give us something stronger. Okay. I only have points and no others then. Yeah, I'm not sure how to answer this question. I mean, the proof is quite formal, so I'm not sure if there's, assuming there's no other objects, if this argument will fail. I think it still holds, but I have to make sure. Sorry. Okay, so yeah, so this is about the algebraic results we need. So now let's move on to the most important part of this talk. So that is understanding the Rouquier dimensions of Fukaya categories. So we introduce notation Wx. We denote by that to be the Fukaya category of the Weinstein manifold X lambda. So all of our main results stated in the first part are proved by either bounding the Rouquier dimension from above or from below using some other geometric quantities. So let me state the results involving upper bounds. So let's assume that the Weinstein manifold X has properly embedded co-core Lagrangian disks. So this is a generic condition, and this is the argument. And this is the condition we need to make this argument to hold. I think this notion first appeared in GPS2 in their statement of generation by co-core statements. So yeah, this is our assumption. So now we consider a generic compactly supported Hamiltonian diffeomorphism phi. And we recall that Cx is the skeleton of our Weinstein manifold. And we consider the size of intersection between the skeleton Cx with its Hamiltonian push-off given by phi. Then this serves as an upper bound of the Rouquier dimension of Rouquier category plus 1. So that's the first upper bound we get of Rouquier dimension in terms of, say, intersections of skeleton. And concerning minimal numbers of critical points of Weinstein lattice vibrations, the statement is the Rouquier dimension is bounded above by this number shifted down by 1. So the third statement regarding upper bound is given by, so let's assume that the Weinstein manifold has actually a arboreal Lagrangian skeleton. I will maybe recall definitions later. And also assume that it emits a good arboreal sectorial cover. So it's some technical condition which allows us to apply the descent formula from work of Galatra, Pardon, Shendig. And also we need to assume that the dimension of this Weinstein manifold is at most 6. Then the Rouquier dimension of the Rouquier category has a uniform bound just in terms of its dimension, half its dimension. Okay, so these are statements for upper bounds on Rouquier dimension of Rouquier category in terms of other geometric quantities. So are there any questions about the statements?
Can I just ask what exactly properties of the generic Hamiltonian do you need? Like, should I be thinking of just sort of non-degenerate critical points or something, or is it
Yes.
something more elaborate?
It's just non-degenerate critical points. So in a sense that the skeleton has a natural stratification in terms of isotropic submanifolds, and there's a Lagrangian piece. So for those pieces which are purely isotropic for generic push-off, they will be displaced from themselves. So we're just considering the intersection coming from Lagrangian part of this skeleton. That's all we need.
I see. Thank you.
Okay. All right. So now let's use the second statement here and try to understand, say, the minimal number of critical points of lattice vibrations over the codinated model S3. So let's recall the statement here. So this proposition says that there exists a pair of formally Weinstein homotopic Weinstein structures, lambda and lambda prime, on the codinated model of S3, such that the minimal number of critical points of Weinstein lattice vibrations over these two Weinstein manifolds are actually different. Okay, so how do we prove that? So we need an input from the work of Eliashberg, Galatra, and Lazarev on flexible Lagrangians. So they construct a Weinstein manifold which is formally isotopic to the codinated bundle of S3 equipped with a standard Liouville form. But for this Weinstein manifold, it actually contains an exact Lagrangian torus. And it could be shown that this Lagrangian torus could be made to be an object of the Fukaya category, so with the brane structure. So in other words, if we look at the Fukaya category of this Weinstein manifold, it has a point-like object, which is given by this Lagrangian torus. Then using one of the properties of Rouquier dimension, we know that Rouquier dimension of Fukaya category is bounded below by 3, which is the dimension of its torus. And also use the upper bound of Rouquier dimension given by this number shifted down by 1. We actually see that for this Weinstein manifold, this minimal number of critical points of a Weinstein lattice vibration is bounded below actually by 4, which is 3 plus 1. And on the other hand, if we look at the standard Liouville structure on the cotangent bundle of S3, so it's actually Liouville isomorphic to the three-dimensional FN quadric. And using this presentation, we can construct a lattice vibration here, which is the projection to the first coordinate, and it only has two critical points. So we know that these two numbers are not the same. So is there any question about this proposition? It's proof. Okay, great. Yeah, so now let's move on to a more precise discussion of our results about the Orlov's conjecture. So let me state the theorem in this way. So let's consider quasi-projective variety Y over the complex field and the field of complex numbers on which admits a homological mirror given by a Weinstein pair of root dimension at most 4. Then it says that the Rouquier dimension of its derived category coherent sheaves is actually equal to the dimension of this variety. So just as a reminder, let's recall the definition of a Weinstein pair. So it says that it is a Weinstein manifold X together with a Weinstein hypersurface embedded inside ideal contact boundary of our Weinstein manifold. So one example of this notion of Weinstein pair would be a Weinstein manifold with a smooth fiber of a Weinstein lattice vibration. So the results one of the results we're going to use is this work of Hacking-Keating regarding homological mirror symmetry of log-Labelle surfaces. Okay, there's a question. Oh, there's no question. Okay. They actually show that one can find some distinguished complex structure on log-Labelle surface on which admits a homological mirror given by a Weinstein pair. It's actually a lattice vibration. And also there's this work of Rouquier and Weda proving homological mirror symmetry with A side given by some F1 and K3 surfaces from millar fibers, and their mirrors could be singular and stacky. So using the mirror symmetry results together with our theorem stated above, we can actually bound the Rouquier dimension of these varieties from above. And the proof of these upper bounds actually use the local to global descent formula of Galashma, Part, and Shende. And also we need some input from symplectic flexibility of the arborization program. So that could, I will talk about that in more detail later. And this gives us upper bounds on the Rouquier dimension of the objects we care about. And just mentioned before, because as long as we have a smooth point of the underlying variety or stack, the Rouquier dimension is bounded below by the dimension of the variety because of the existence of point-like object. So combining the upper bounds given by, say, mirror symmetry and symplectic geometry, and the lower bounds given by the existence of a point-like object in derived category coherent sheaves, we can actually conclude that for these examples, Orlov's conjecture holds.
When you say homological mirror, do you mean like in the sense that there's a pair where you have homological mirror symmetry?
Yes, in a sense that there's a Weinstein pair, you can consider this partial Fukaya category that's actually, say, equivalent to the category coherent sheaves over Y. So that's what I mean by homological mirror of this Y. So any other question about this theorem and the explanations later on? Okay, looks no. So now let me move to, say, the estimate about lower bounds of Rouquier dimension of Fukaya category. So here's the statement. So let's take the Fukaya category of Weinstein manifold X, and we suppose that we can find a split generator of this Fukaya category with the property that actually it should be the cohomology of this object with itself is actually a Noetherian module over subring of the Smecker homology. So here, R at the subring of snack homology acts on this Hom space via the closed open map. So yeah, because snack homology is ring structure, we can talk about subrings inside there. And this is a module over on the speckle homology. So we can talk about this as a module over the subring. So then statement is the Rouquier dimension of Fukaya category is actually bounded below by the Krull dimension of this vertical homology over the ring R. So this is the more general statement which we'll cover on the previous two similarly different results regarding quantitative intersections of skeleta. And here's some more explanations. So let's consider the Z-graded case, namely 2 times first term class is trivial. Then if we assume that the degree 0 part of the speckle homology is isomorphic to the Fn coordinate ring of a smooth Fn variety over C, and assume that K is actually a homological section, then we know that K is a split generator on this proved by Power-Linello, of course, and also by assumption on this degree 0 part of speckle homology is actually isomorphic to the cohomology of K with itself, and we assume that it's actually isomorphic to the Fn coordinate ring of a smooth Fn variety over C of dimension n. So in particular, we know that the Krull dimension here is actually given by n. So by applying this inequality, we conclude that the Rouquier dimension of Fukaya category is bounded below by n. And recall that the Rouquier dimension of the Fukaya category is bounded above by the intersection of the number between the skeleton and the generic Hamiltonian push-off, -1. So this lower bound together with the upper bound I stated before gives us this quantitative intersection result. So any question about this theorem and the illustration of this example? Okay, seems no. And then let me say how to apply this results about lower bounds to the case of cotangent bundle of Lie groups. So recall that the G here is assumed to be a compact, simply connected Lie group. And we are interested in, say, taking an arbitrary Weinstein structure on the cotangent bundle of the Lie group G, try to understand the Rouquier dimension of the Fukaya category. So the point is we need some computations from rational homotopy theory. So let me introduce some notations. So let Lm and respectively omega Pm to be the free and base loop spaces. So the base point here is P of an n-dimensional manifold, closed manifold M. So now we can consider the homology of the free loop space and base loop space. So there's a notion of intersection morphism introduced in the work of Chess and Sullivan on string topology. So morally speaking, we know that the base loop space stays as inside a free loop space as submanifold with finite codimensions. So for this pair, one can define the so-called runway map or Umker map from the underlying manifold on the free loop space of M to the base loop space. So it's some kind of topological construction between this pair of spaces. And in the work of Apododo-Schwartz, they actually show that this intersection morphism coincides with the closed open map if we use it isomorphism identifying, yeah, I ignore the complexity from local system gradients here. So it coincides with the closed open map if we use isomorphism between the homology of free loop space and speckle homology of cotangent bundle, and the isomorphism between the homology of base loop space and the wrapped circle homology of the two-tangent fiber. So in other words, our previous statement is about something related to the properties of closed open maps. By using these two isomorphisms, we can translate the property of this intersection morphism into the properties of closed open map. Then go back to our context. So we are looking at simply connected compact Lie groups. So it has a rational homotopy type given product of odd-dimensional spheres. And because then we can just work over Q and use this rational homotopy type to make our computations. Then the main point is we can compute that the Krull dimension of the homology of base loop space of this group G over some subring R of the homology of free loop space is actually equal to the rank of this Lie group. So as before, we know that the Rouquier dimension +1 is bounded above by this intersection number. And on the other hand, using this lower bound coming from estimating the Krull dimension of this guy, we know that this intersection number overall is bounded below by the rank of this Lie group +1. So is there any question about these arguments? Okay, seems no. Okay, now let me move to the fourth part of this talk. I will present the ideas of proofs of some of the results stated in section 3. So the first thing I want to talk about in this section is on the generation of intersection, quantitative generation from intersection of skeleta. So here's the setup. So still, we consider a generic complex supported Hamiltonian diffeomorphism of our Weinstein manifold X denoted by phi. And we consider the Weinstein manifold equipped with this Liouville 1 form. So on the first coordinate is given by the negating the Liouville 1 form, but on the second coordinate, we need to pull back the 1 form using the given Hamiltonian diffeomorphism. So inside this Weinstein manifold, we can consider a special Lagrangian, which is diagonal Lagrangian. And the special feature of this particular Liouville 1 form is the diagonal Lagrangian will actually intersect the skeleton of this Weinstein manifold only at Cx, the core of this Weinstein manifold, and is considered the intersection with this and Hamiltonian push-off. They will just intersect, the diagonal will just intersect the skeleton at these many points. So this is just a simple geometric observation. Then we can invoke the work of Ganatra, Paulin, Shende, or Chandrin, Dmitry Golov, Rizzo, Gigini, and Golovko. So their results on their proof of the generation of replica category of Weinstein manifold by co-cores could actually tell us that this object, this diagonal Lagrangian, is actually quasi-isomorphic to an interrelated cone of product of co-core Lagrangians of length given by this number. So in other words, we can resolve the diagonal Lagrangian by product of co-cores, and the number of co-cores we need to take is this number. Okay, so now we have a geometric resolution of a diagonal, and to compute, to estimate the Rouquier dimension, we just need to turn this to a resolution of the corresponding bimodules. So here's a statement, and it should be well known to experts. So it says the following. So there is a fully faithful infinity functor from the replica category of this Weinstein manifold to the DG category of bimodules over the replica category of ordinary Weinstein manifold, satisfying the following properties. So the first one says that the diagonal Lagrangian as a Lagrangian is actually taken to the diagonal bimodule under this infinity functor. And if we have a, say, a product Lagrangian, then it's taken to the unetta bimodule. So this is a step about, say, translating the resolution of the geometric diagonal Lagrangian into a resolution of diagonal bimodule in terms of unital bimodules. So the proof, well, essentially is the same as in Shill's thesis, but Schill used this quadratic setup. But in GPS2, they actually have the unital functor, which almost suffices for our need, but they didn't include the diagonal Lagrangian. So in any case, well, the ingredients of the proof proposition are already there. So it's just a combination of this correct localization setup in GPS2 with ideas from Shill's thesis that will suffice us to prove this proposition. Yeah, as I said, this allows us to obtain the resolution of diagonal bimodule by unital bimodules from the geometric resolution we said before. Then we know that the diagonal Lagrangian could be resolved by unital bimodules with at most these many steps, and this could serve as upper bound of the Rouquier dimension +1. So we conclude that this geometric quantity could serve as upper bound of the Rouquier dimension of the replica category +1. So any question about this? Okay, seems no. So then let me move to the next part. Let's consider lattice vibrations. So we start with the Weinstein lattice vibration, and we denote by F. It's smooth fiber, and we use a notation CF to denote the skeleton of the fiber. Then we can use the work of Part and Shende on presenting the replica category of the Weinstein manifold X as a localization of the partial replica category of the pair X and the skeleton of F. Then recall that we have the monotonicity of Rouquier dimension on the localization or on the quotient. We see that the Rouquier dimension of the partial replica category serves as the upper bound of the Rouquier dimension of the replica category of the underlying Weinstein manifold X. So now let's try to understand the Rouquier dimension of this partial replica category. The point is the lattice symbols of this lattice vibration actually could give a semi-orthogonal decomposition of this category. And use on our previous your statement we recall before, we know that this semi-orthogonal decomposition could be used to give upper bound of the Rouquier dimension of this guy. So this is exactly the inequality we will get. It's telling us that the Rouquier dimension of this guy is bounded above. So we can choose arbitrary, say, Weinstein lattice vibrations. Then we take the minimum. So this is this gives us the inequality. This number -1 could serve as an upper bound of the Rouquier dimension. And we know that this category localizes. Could be localized to give the replica category of the Weinstein manifold. And using this monotonicity inequality, we simply see that this number could be served as upper bound of the Rouquier dimension of the replica category of X. So any question about this part?
Can you say again why the semi-orthogonal decomposition implies these statements? Just like a quick reminder.
Yes. So we know that we have a semi-orthogonal decomposition with each local piece given by the subcategory generated by lattice symbol. So for each local piece, it's on the corresponding local category is actually the digit category of modules over the underlying field we work with. So for this guy, the Rouquier dimension is given by 0, because you can more or less think it as a representation category of the A1 quiver. And on the other hand, we know that this semi-orthogonal decomposition has length given by the number of critical points of lattice vibration. And we recall that in this inequality of bounding Rouquier dimensions by these local pieces, there is a shift +1 for each local piece. So that shift by 1 contributes to the lattice number here. Lattice number of critical points lattice vibration here. And there's overall shift by -1. So that's why we have this inequality.
Thank you.
You're welcome. Okay. Then let me go to the next part, which is about bounding the Rouquier dimensions from above using yet another input from some of the very recent work on symplectic flexibility. So before discussing things in full generality, so let's consider an example which might illustrate what we are doing in general. So here's the setup. So let's consider a closed n-dimensional smooth manifold M, and we consider smooth triangulation of M. So because we have this triangulation, we can talk about simplices inside this triangulation, and we just take all the 0 simplices. And for each simplex, we can consider a star, namely all those closed simplices which contain this given simplex as a subcomplex. So we just take away all the 0 simplices and consider an inward smoothing of this closed star. So using these codimension 0 submanifold with boundary, they could form a cover of our smooth manifold M. Also, it has a nice property of the depth of their intersection. So suppose that we have a sequence of of these subsets of M. If the intersection of this tuple is actually non-empty, then we know that this depth of the intersection is bounded above by the dimension of our manifold +1. This is just given by the nature of triangulation. Also, if we choose the smoothing of the boundary of these stars carefully, we can actually make sure that the boundary of them actually intersect transversely. So then the point is, if we take the cotangent bundle of this submanifold with boundary, they could actually form a sectorial cover of the cotangent bundle of M in the sense of the work of Ganatrov, Parda, and Shende. So the point is, there's a descent formula of GPS2, which tells us that the Fukaya category of cotangent bundle of M could be recovered as sort of a homotopic limit of these kind of local pieces coming from intersecting these codimension 0 submanifolds. And then there is generalization of the inequality of Rouquier dimension coming from semi-orthogonal decomposition to this more general form of Groton deconstruction that allow us to use this local to global principle to actually obtain the inequality that the Rouquier dimension of cotangent bundle is bounded above by the dimension of the underlying manifold. So it's an argument using this descent formula. So this is a case for smooth manifolds. And for general Weinstein manifolds, we also want to apply these ideas. So the point is we want to construct good covers. Good in a sense, I will try to make more precise later. And we want to use this descent formula from the work of Ganatrov, Parda, and Shende to understand the Rouquier dimensions of the Fukaya category. So the main technical input of this part is the recent work by Alvarez Gavela, Eliashberg, and Nader about optimization of Weinstein manifolds. So one really rough statement of their result is given a Weinstein manifold, also we assume that it's endowed with a global Lagrangian plane field, then this Weinstein manifold is actually Weinstein homotopic to a Weinstein manifold whose skeleton only has a restricted class of singularities that's called arboreal singularities. So I will now define what arboreal singularities are, but they have some nice properties that we can use. So the point is, for these arboreal singularities are actually indexed by rooted trees. And they also arise as skeleta of some kind of distinguished Weinstein sectors. When I say Weinstein sector, we just mean the class of Weinstein manifold with boundary with well-behaved holomorphic curve behavior. And for these sectors associated to trees, to rooted trees, their replica categories are quite simple. They're just quasi-isomorphic to, say, perfect modules over the corresponding path algebra of the quiver, where the quiver is the underlying quiver of the rooted tree. Then using the result I recall before, we know that the Rouquier dimension of this Weinstein sector is equal to 0 if the underlying quiver is actually of ADE type. Otherwise, it's given by 1. Then just following the ideas in a smooth case, in some sense, we want to triangulate the arboreal skeleta of Weinstein manifolds with the following properties. So we can take the stars of all the simplices, and they should actually be the skeleton of some Weinstein sector for some rooted tree. And also we want the boundaries of these stars to intersect nicely as in the smooth case, because we want to really construct sectorial cover of our Weinstein manifolds given by these local pieces. And also because this cover comes from a triangulation, we can get we can actually control the depth of this cover in terms of the dimension of the Weinstein manifold. Then we can incorporate the descent formula from Gadacha-Partin and Shende, and the upper bound from Rouquier dimension from Groton deconstruction, which is a generalization upper bound from a semi-orthogonal decomposition, and show that the Rouquier dimension of this Weinstein manifold is bounded above by half its real dimension. Because for any tree with at most 4 vertices, the underlying any quiver associated that must be of ADE type. And we know that the Rouquier dimension of the corresponding representation category is actually 0. So as a technical remark, so our current result restricts to the case when it's less than or equal to 2, but it could be generalized in principle. Maybe it's also possible to use sheaf theoretical methods to avoid the discussion about constructing a sectorial cover of the Weinstein manifold. We can just restrict ourselves to a cover of a skeleton. So any question about this part? Okay, seems no. So I have 2 more minutes. Let me just point out 2 questions which I find interesting. So the first one is the following. So given a triangle category, we can consider the collection of all of its generation times, in the sense that generation times of shifted down by 1 by all of its split generators. And this set is actually called the Orlov spectrum of a triangle category. Then the question is there any way to understand the geometric meaning of all the spectra of replica categories beyond the minimum one? So minimum one is the Rouquier dimension, and we know that it has some geometric importance. And the question is, how about those higher ones? And the second question is, so based on our covering approach to bound Rouquier dimensions from above, we can ask how to define a notion of a Lustenik Schneiderman category of Weinstein manifolds based on arborealization. And how is this related to the cone length of underlying topological space of our skeleton? Okay, so those are two questions I put here. And so that's all of my talk. So thanks for your attention.
Great, let's thank Shaoyun for the great talk. Thanks so much. Are there any questions for the speaker?
Yes. So I have a question about the like bounding the minimal critical points of a Lifshitz vibration. Like,
Okay.
according to your result, like combining with a result of, I guess, Oleg Lazarev on the, I guess, an upper bound of the minimal number of Weinstein-Morse function, does your result imply that for specific examples, like you mentioned that special T star S3, like you get exactly the minimal Morse number of that T star S3, or maybe other examples?
Yeah, I'm not sure because in our case, we care about critical points of coming from Lifshitz vibration, but in Lazarev's case, he cares about general Weinstein-Morse functions. So I think there might be some kind of inequality relating this quantity to two quantities, but it's not so clear to me how to really prove that this number is exactly equal to that using Oleg's work.
Okay, thank you.
So is Orlov's conjecture known for toric varieties? Yes, I think it's known for toric funnel guys up to dimension 3. And for maybe in dimension 2, also known for all toric varieties. But in dimension 3, it's just known for funnel ones.
Well, presumably, like your method then implies it for at least all toric phonos, right? If you do this, apply homological mirror symmetry.
Yes, so providing that we can make argument work in dimension 6. So in that case, it's not just for funnel ones, it works for all toric guys.
Yeah.
Mm-hmm.
Wait, sorry. So your argument, maybe I missed that. So your argument was only in low dimensions. It was only, so like this, like homological mirror symmetry state, like if you have a homological mirror, then you have, that was only in low dimensions.
Yeah, the problem is, we want to understand how to bound the Rouquier dimension from above. And there's an important result we need to use is if we consider the representation category of a quiver of ADE type, its Rouquier dimension is given by 0. So for general quivers, the Rouquier dimension is given by 1. So the dimension factor here, the dimension constant here actually appears as a depth of our cover. And this is the upper bound we want. So if we have a local piece which contributes positively to Rouquier dimension, we will get a weaker bound. And we restrict ourselves to dimension at most 3 because all the underlying trees of the arboreal singularities are actually of ADE type if they have at most 4 vertices. So for higher dimensions, if you can construct a cover with arboreal sectorial cover such that each of the associated trees are of ADE type, our arguments also go through.
I see. Thanks.
So does this knowledge of Rouquier dimension, does that allow you to like prove or disprove examples of homological mirror symmetry? Like if you can show that they're different on DB-Co and the Fukaya category?
Yeah, I guess so. If you have a pair and you don't know a priori if they're mirror to each other and you compute their Rouquier dimension, if they're different, of course, the corresponding categories are different. but I don't think this is a good approach to disprove mirror symmetry. But yeah, maybe.
Are there further questions for the speakers? Okay, well, let's thank Shaoyun again for the great talk.